Hello everyone. My name is Bhavya Deeprai. Welcome to the week 5 problem solving session. Right now the week 5 problem session had been rescheduled to from Saturday to today, 2nd of March, from Tuesday to the 2nd of March, that is Saturday. So maybe there was a misinformation, or rather, there was no reminder regarding the rescheduling. So I think there are no current students coming to the session right now. But it's okay. Will the session is still recorded, so it's getting uploaded. It will get uploaded after the session is fully recorded. So, but I'll continue, and I hope that you guys can see the recording. So, okay, let us begin. So, week 5 was mostly based on, again, push down automatas and CFLs. So, what did we see last week? Let me let me duplicate this page. Okay, and delete this. So last time, what did we see? We saw CFLs, context-free languages. And what are context-free languages? They are those languages which can be generated by what are called context-free grammars, right? Now, what are context-free grammars? They are grammars. They are a tuple of this form VSTP, where V is the set of variables, S is the set of it's the start state, uh, T is the set of terminals, or S can be called as the start variable, and P is what is called the production rule. Okay, and production rules are of the following form: S gives AB and A gives B A, where A and B are variables, and the small a is the terminal. They are constants, in other words, right? And variables are capable of generating uh, other variables or terminals. Next, what will we do? uh, Next, we saw in this week that PDAs, push down automata, are equivalent to, or the language computed by PDAs the language computed by PDAs is nothing but CFLs, and CFLs are also language computed by PDAs, so can be said to be equivalent. This was the equivalence we saw in the lectures, right? Now, what about PDAs? Now, PDAs can be thought of TFAs or finite automata. Okay, I'll remove the just finite automata. We remember what finite automatas were: that had states, symbols, and so on, and transition table that move from one state to another. But finite automata, we can think of them as finite automatas with a stack. Okay. Now, what do you mean by stack? The stack is a kind of data structure where you can push and you can pop. And you can pop meaning you can delete, push meaning you can insert, and pop meaning you can delete. And both you can do only on the top element of the stack. And so this is also what is called the last in first out data structure. Whatever you entered last is the only element that can be popped out first. Okay. Now, why is it called a push down? Well, one way to think about it is that you are pushing down elements into the container, or actually, this push down is another name for stack. Push down. They said that this is what the British mathematicians called a stack, and stack is what the Americans called the data structure. But stack is what is more popularly used. So anyway, so what is important is now we have a stack here. So we have a memory here, which is still a bit restricted, right? If you look at DFAs or FAs, finite automata, their memory is very restricted. In what sense is their memory restricted? Their memory is restricted in the following sense that states are used to remember. But in a PDA, you have the stack. So since states are used to remember and there are only constant number of states, finite number of states, the memory is very finite. But stack can grow very large, need not be constant. So here and but still restricted by push and pop operation, right? So and this is the difference. And now before we've seen that, we've already seen the following. We've seen that the language a to the n, b to the n is not in regular languages, and but a to the n, b to the n is in context-free languages. So this already shows that PDA is more powerful than DF. This already shows this. Okay. Now that's what we want to do. We want to restrict the memory lesser and less. Okay. Now that we had this small recap, I want to first discuss some of the assignment questions. So week 4 questions. I won't discuss all the questions, but I will just discuss questions that are that seem to be on the more tougher side in the assignment. Okay. Okay. So here's the first question. The first question says the following: recall the condition under which PDAs accept strings. Okay. So this is the PDA. So yeah, you have the stack, you have the symbols, you have the stack symbols, and so on, and final state, and the PDA accepts an input string W. When is it set to accept the string W? When okay, Wi belongs to the set of alphabets. This is alphabets union sigma empty, right? And sequences R0, R1, and so on till Rm. Okay. And S0, S1, Sm in sigma star. So what is this? This is the stack contents of the stack contents. So you can think of S0, S1, and so on, okay, being the stack. And what is this? R0, R1 are uh, this is the sequence of states, okay, during computation given an input. Okay, so for example, in a DFA, you can imagine like this. So for a DFA, we were saying if there exists a sequence such that S of m is the final state, right? That is what is happening here. Um, so that was what we were saying in the DFS case. But in this case, um, we are generalizing the notion to PDAs, right? So we are saying, okay, this is R0, the first state should be a start state. R0 equals Q0. And S0 equals epsilon. What does this mean? This means stack should begin with the end. Stack should be empty in the beginning. It has epsilon. Now, for I equals 0, 1 till m minus 1, okay, what will we do? If, okay, we in a state Ri, rather, if on a state Ri, okay, this is a transition function, right? So on a state Ri, we read the symbol Wi plus 1, okay, because this is the input, right? If we were in W1, we read W2, that's what, right? If we read Wi plus 1, and A is at the stack, current stack top. If on the top we see an A, then what do? You do AT, SI equals AT, meaning, oh, okay, and SI equals AT, sorry, SI equals AT, current stack top, same thing, okay. This is the string that the stack contains, A followed by T. Now T is whatever remains, okay. Okay, yeah. Then what are you saying? You move to the state Ri plus 1. You move to the state Ri plus 1, and what do? You push B onto the stack. How? Because the new value of Si plus 1, which means stack content at the after reading input I plus 1, okay, should be BT. Getting it? Okay. So, it means you've popped A and pushed B. Popped A, push B. Okay. Now, what we do is we do a redefinition. Okay, and finally, this is a final state, and the final RM. Okay. Oh, sorry, made a mistake here. This shouldn't be S. The S is the stack context. R0, R1, RM should be the final. It should be the sequence of states on that input, and the final state RM, the last state encountered should be a final state. Then it is set to accept. Also, if you remember, there are two definitions for acceptance in a PDA. The first definition for acceptance is if you reach a final state. The second definition for acceptance is if the stack gets empty at the end. Both are equivalent. If you've seen the lectures, then you'll recall that either definitions are fine. Okay. Now let's look at this. We define a push through automaton. Okay, this is the new name. A push through automaton. Now let's see what's a push through automaton. As a PDA with a queue instead of a stack. Okay, we've removed the data structure of a stack and made it a queue instead. Okay, and what do you say? We say that, okay, since PDA computes CFL, the language computed by a PTA, push through automaton, is what is called a PTL, push through language. Okay, as any language that can be recognized by a PTA, that is, instead of pushing and popping values from the front of the stack, Okay, what is a queue? Instead of pushing and popping values from the front of the stack, values are pushed from the front and popped from the back. Or to make things simpler, let me write it as pushed from the back, its equivalent, and popped from the front. This is the usual description of a queue we have heard of, right? So if this is a queue, we push from the back and pop from the front. Getting it? Okay. And next we define. Okay, so that is the first thing. Next, what do we do? Okay, so this is the formal definition, and you can analyze it, and you can see that this means nothing but a queue, because instead of BT you are doing TB. Means that if you see an A, pop the first element and put a B. Okay, which means you've popped from the front, pop A from front, push B at back. This is what is happening. So you have A, you had A in the beginning and T here. You popped A and then put B at the back. You got TB. Okay. Next, we also define a two-stack PDA. Now, what is a two-stack PDA? As the name suggests, PDA with two stacks. So imagine a machine M. Okay, this is the first machine. Okay, this is a PTA. What does PTA look like? A PTA, instead of a stack, okay, instead of stack, has a queue. So this is a queue. Okay, and next, what do you have? A two-stack PDA. Now, what is a two-stack PDA? This is a machine, and instead of a queue or a stack, you have two stacks. Now, let me call it stack A, stack B. But both are behave like stacks only, simple normal stacks. Okay. And here we can see the definition. It's gamma square this time, meaning we need one additional element in a tuple to describe what the top value of the two stacks are. We need to keep track of the value of the top elements of the two stacks. And as the automaton must now read and write one value from each stack, the definition of acceptance can also be modified appropriately. So yeah, the definition of acceptance can be modified appropriately. You've already seen what that means. It just means that you can either say that both the stacks are empty, or you can sometimes even define as one of the stacks is empty and then empty the next stack, or you can say that final state is reached. Final state is reached, then the stack accepts. Okay, so now I think this is clear what the question says. Moving on, we will address questions like regarding the power of the machine. Okay, so we'll address questions regarding the power of the machine. Given a queue, will it be more powerful? Given a stack, given two stacks, will it be more powerful than PDA? PDA is just a machine with a single stack. Okay, let's look at the first question. Which of the following languages are PTLs? Select all that apply. Okay. Yeah. Okay. Firstly, what we want to do is I want to clarify one thing, that you can see that it says it belongs to delta Ri and so on. So what does this mean? Since I have a belongs to and not equal to, this means that this is a set. Delta something is a set. What do I mean? Sorry. What do I mean when this guy is a set? The delta is a set. it means that the transition function could be moving into multiple states. Okay, so what does this mean? Delta, okay, delta um, taking delta takes ri wi plus 1 a and maps it, can map it to multiple ri plus 1 b, can map to multiple states. Okay, what does this mean? What does this mean if it can map to multiple? It means that machine PTA is non-deterministic. So we have the power of non-determinism with us. It is not well defined in the question that the machine is non-deterministic. So we can observe it here that because we are talking about belongs to, it means the machine is non-deterministic. Okay, and here too it is. So this means that machine is, or let us call it 2-stack PDA. Okay, 2-stack PDA is non-deterministic. Okay, okay. Now let's move on. First question is as follows: W square such that W is in sigma star. Now, question is this language PTL, or if can we ask even whether this language is PD? The problem with having trying to use a PDA for this is that okay, let's call it problem E. W square W in sigma star. Is this in PDA? Can this be? This is a CFL. This is the first question. Well, this is not possible. It can be shown that this is not possible, but it is possible by a non-deterministic CFL. Right. And how do you do that? Well, you keep pushing onto the stack and non-deterministically choose when we are at the end of the first W. We keep pushing elements 0, 1, 0 and so on. And oh sorry, W reverse. Okay, is W reverse in CL. Okay, yeah. And what we did was, yeah, and as we saw, and non-deterministically choose a point, and if the point chosen was here, then we'll see exactly W reverse out here. Compare with W reverse and then pop. Right. So WW reverse is NCF is possible by NCF. Similarly, we'll use a similar logic. Okay, to handle the case of Q for PTA. That is, we have a Q now. That is, we have a Q now. So, what would be the strategy for this? So, what we do here is, okay, construction of PDA is as follows. Okay, what we do is, for all input symbol, push symbol on stack. Okay, during this we non-deterministically, okay, decide whether all of W is encountered or not. I'll explain what this means. And finally, what we do is pop from front. Okay. Now, okay, what do I mean by all this? The idea is as follows. Say we want to know whether 101 101 is in the language or not. It obviously is. Now let's say we want to use a queue to store it. So let's say I want to remember up till this point, right? The most logical thing to do would be remember up till this point, 101. Then from what you've remembered, compared with this point. Well, what I can do is I can store 101 in the queue. Then what I can do, right? 101, the first part is in the queue. This is the queue. First part is in the queue. Next, what do you want to do? You want to compare whether the remaining part of the string, WW equals, you want to compare whether the remaining part of the string actually corresponds to this. So you can check whether, okay, 1 is equal to 1, then pop from the queue, 0 is equal to 0, then pop from the queue, 1 equals 1, then pop from the queue. Right. But there is a problem. Well, problem is, how do you find this partition? Finding partition. When do you know when W stops? That is, how do we know when W ends? How do we not? How do we know? Like, if I had put a partition here, then I would put 1 0 in the queue. Then I would compare with 1 1, and already I would reject the string because I had considered this to be W and this to be W. But this was clearly a wrong partition we did. No, we did not find the right partition. How do we find the right partition? What we'll do is solution is partition, or rather fixed partition, non-deterministically. If we non-deterministically fix the partition, then there would be several computation. That is, I could partition, okay, the first partition could be something like 10101, 101, 101, right? 101, 101, 101, 101, and so on. The first partition could be something like this, second partition could be something like this, third partition could be something like this, and so on, right? And non-deterministically partition it, and this is going to say reject, this is going to say accept, and that is good for us. This is going to reject. And what do you observe? If string is of form WW, then at least one partition is accepting okay, not accept, is accepting, leads to accepting path, right? This is the definition of non-determinism. So therefore what we do is, for all input symbol, just push the symbol. So like we did 101, right? We pushed in. Now what did we do? We every time we push symbol on task, during this non-deterministically decide whether all of W is encountered or not. Okay. And let's say, and non-deterministically, so here we assume this is W, here we assume this is W, here we assume this is W. And what do? Pop from front when input symbol matches with front. And what otherwise? If no, reject, right? And if stack empty, accept, otherwise reject. I'll give you an example. Let's take 101, 101 only. 101, 101. Okay. Now here 101. Right, we have 101 here. I'll push that onto stack 1. Then we say push 1, 0. Then push 1 on the stack. At any point in between, we could have non-deterministically said, oh, okay, this is the end of the stack, then we start the next operation. But let's say we consider the case when this is where the partition is. Partition. We assume this is the W, the first part. Then what do? Next, what are this bunch of strings we see next? We see a 1, we see a 0, we see a 1. If we see a 1, we see a 1 here, pop. We see a 0, we see a 0 here, pop. We see a 1, we see a 1 here, pop. The stack is empty, then reject. Okay. So we saw that it is possible to actually design a push through language for W square. Okay. Okay, before doing e to the 2 to the n, I'll first do W cube and W1 W square, W2 square. Okay, because they are of similar flavor. E to the 2n requires slightly more creativity. Okay. So W cube. If now that you've seen the W square, right? W cube will be of similar flavor. So here's how you do it. Okay. Idea is again similar. Now that we know how to use non-determinism to detect where W ends. Okay. So this is a queue you have. What I'll do is, as I see W, okay, I'll store it in the stack. Okay. And next, what do? As I see, there could be multiple strategies, but one strategy you can come up with is, as you see the next set of W, okay, this is the first queue, first W. For the next set of W, what you do is you pop if it matches, okay, and push it at the back. Okay, pop if let's say pop if, let's call this, see if it's W1, W2, W3. Okay. Pop if, okay, let's not, okay, let me call it UVW. Okay. Okay, this also has a W, so let's write it as WXY. Okay, this is best. WXY. Okay. And pop if we put W in the beginning, right? Now we need to compare if the first symbol of X is equal to the first symbol of W. And pop if, W's first symbol, okay, or ith symbol is equal to the input ith symbol that we're getting. We need to compare this one with this one. right? And if so, keep pushing. If no, then reject. What do I mean by reject? You can either think of emptying the stack, going into a state such that the stack will get always emptied, or you can think of going into a reject state and keep looping. Okay, and we do this. So what do we end up with? What do we end up with? We end up with uh, if all's good, then we end up with W again. We end up with W again, right? For the last, okay, first W for the last W, or since we've written W as next X, then last Z part, okay, Y part, this part. For the last Y, again we compare. If again do the same thing, but this time only pop. Pop if Wi equals, okay, equals Yi. Then if no, then reject. Then what do you have? Okay, now let's analyze this. Okay, so you get a W which is something like 10110. Okay, 101101101. This is valid because see, this can be taken as W, this can be taken as W, this can be taken as W. But let's say we don't know whether all are W's, and firstly, this partitioning can be done non-deterministically. So this is all the time working non-deterministically. What do I mean by working non-deterministically? This knowing where to stop analyzing W, that is chosen non-deterministically. Okay. So yeah. So let's see what happens. In some, so you may have pushed 1, 0, and at this point you decided to partition it. Okay, this is one non-deterministic configuration, and this will later lead to reject. Okay, but there is at least one non-deterministic case where we partition exactly at 101, and this is what we want to follow. So, and one where we partition at 1011, and another where we partition at 1. So this is non-deterministic partitions for obtaining W. Okay, and let's say we get 10110 and so on, but this is good for us. Okay, and we need to accept such instance. Now it trivially follows. Why? Because now what happens? Now what happens is, what we are seeing is we put 101 on 101 on the queue. Next, what do we do? For the next X part, we compare. We compare 1 is 1, good. Okay, and put it at the end. We compare, okay, 0 equals 0. This 0 equals this 0. Good. Put it here. And next we compare, okay, 1 is equal to this one. Okay, this one. So pop it and push it back. Now we've established WW, while also not forgetting what a single W was. Next we compare with 101 at the end, this W, what we do is, oh, okay, one, okay, this is what, this is y, right? Now, y, the first symbol in y is equal to this first symbol on the q, right? Pop, pop next because again 0 matches with 0, and then pop again because 1 matches with 1, and this is empty, and this will get accepted considering the condition of acceptance is that the stack is empty. Okay, next question is, so this is also possible. Now let's see, w1 w2 square, is it possible? w1 w2 square, where w1 w2 both are strings. Now we can quite easily answer this question. How can we answer this question? Well, we know how to do w2 square. This is nothing but same as part A. We know how to do this. How are we doing this? Well, we store w2 on a queue. Okay, we store w2, and how do we find w2? Choose the partition, choose where w2 ends non-deterministically. Same as part A. How? w2 w2, choose this partition where w2 ends non-deterministically. Where w2 ends non-deterministically, and once w2 ends, and push w2 to q, and pop from q as we see next w2. So let's say after pushing you get w2, and then we'll compare with the input whether it matches here, then pop, matches here, then pop, and so on, and then this stack becomes empty. This is how we solve w2 or w2 square. Part A was w square, so same thing. Now the problem is, this is creating a problem, w1 followed by w2 square. Right? How do you do this? Well, since the problem is as follows, that we don't know where w1 ends and w2 begins. We don't know where w1 ends and w2 begins. Right? But we've encountered this problem before. For example, here, we didn't know where w2 ends and the next w2 begins. Same thing in this one. We didn't know where the first w ended and the second w started and the third w started. We didn't know. But how did we cope with it? We coped with it by using non-determinism. Again, use non-determinism. Now, how do you use what do I mean by when to use non-determinism? Again, choose where w1 ends non-deterministically. Well, it might sound pretty abstract how you can choose to do it non-deterministically in terms of the machines, in terms of a DFA or PDA, but similarly, I mean, it just looks like this. It looks something like this. Okay, it looks like you have q0, and on 0 1 you simply loop, as well as on 0 1 you move to a new state. Okay, new set of states. This does something. But here what is happening? This is where the choosing is happening. Whether you see a 0 or when you stay there in the same state, or you choose to partition now. What happens here? You could either have, what are the possibilities that if you have 101, 101, 101, then you could have taken the first one, okay, and then done a 0 1 1 0 1, okay. You could have chosen 1, okay, you could have looped on 1 and then remaining 0 1 1 0 1 0 1 and so on, and this is where you partitioned it, getting it? And similarly another partition would be like if you looped on 1 0, okay, and the remaining portion you did 1 0 1 0 1 1 0 1 1 0 1, sorry. Right, this is another partition and so on. So this is how you partition, and at the same time you will give an instruction, okay, whether you get a 0 or 1, you just push it onto stack. If you see a 0, if you see a 0, then push a 0 to a stack, okay, and if you see a 1, then push a 1 to the stack, okay, or I'll just write it in words: 0, then push 0, 1, then push 1, something like this. So this is what I actually mean by, non-deterministically choose a partition and so on. Okay, now that's fine. Now we use non-determinism to select a partition for W1. We select where W1 ends, and after selecting where W1 ends, we choose non-deterministic, and by then after that we get where W2 begins, and for W2 also we non-deterministically choose where W2 ends, and we know how to handle W2 square. We saw it in part A, okay, using the Q. So hence, if a word, a string is of the form W1 W2 square, then definitely at least one non-deterministic path except. Okay, one non-deterministic sequence of choices will always choose the right partitions, and then it will finally detect that, oh, okay, the machine is of the form, the string is of the form W1 followed by W2 square. Okay, very good. Um, finally, um, okay, finally, this is the question. Okay, so this is done. So e to the 2 to the n. How do you handle that? This is at a to the 2 to the n. M is a natural number. Now we've known how to do non-determinism and how to use Q in clever ways. So we'll see yet another clever way, a more clever way to actually do this. Okay. So the push-down automata sees, okay, this A, and so on. Okay. And this is some K. Question is K some 2 to the n? Is it a power of 2? Is K a power of 2? Okay. How do you determine that? So here is a technique to do it. Idea: push all of input to stack. Push all of input to stack. Okay. Now, what do we want to do? Simulate repeated division by 2. How? Pop 2 A's from back, push single A at front. Okay. Now what do I mean by this? Oh, so first of all, why do you want to do repeated division by 2? Say your input is a power of 2. Okay. Take any power of 2. Okay. Take any power of 2, let's say 16. 16 can be divided by 2 into 8. Divide by 2. Divide by 2 into 4. Divide by 2. What do you get? 2 and divide by 2, you get 1. Right. And again, if you do 32, then again, and so on until 1 divide by 2. Okay. And so on. In fact, if you do this technique of popping 2 A's, okay, each time, popping 2 A's each time, and you are if you have 2 A's remaining at the end and you pop both of them, you get the stack as empty. So this is the kind of logic that we want to come up with. Okay, so here is the procedure. So here I'll demonstrate how we do it. So what is step 1? Step 1 is push all the inputs to the stack. So I put A, and so on till A. Right. I push all the A's into the stack. And let's say this is some 2 to the n. Let's say it is some 2 to the n. Okay, in many. Next, what do you do? Next, what do you do? You remove 2 A's, put 1 A in front. Okay, let me do a different color. Next, what do you do? After that, you remove 2 A's, put 1 A in front. And you keep doing this. Okay. Now we observe that if, say, exactly 1 A is remaining, if we cannot pop 2 A's, what does it mean if we cannot pop 2 A's? It can only happen if a single A is remaining. Only single A remains. If only a single A remains, this means that K is odd because it should have been divisible by 2. We could partition it into groups of 2's. So then we reject. Okay. Otherwise, what happened? Otherwise, it was even. And process continues. Question is, what is the number of filaments in this half, in the left portion? Since for every 2 A's, we put a single A on the left, there are exactly half many A's. So here how many will be there? K by 2, which is nothing but 2 to the n and so on. Now what do you do? Repeat process on. Oh, okay. Now what do you do? So you want to repeat the process. You want to repeat this process. Keep doing it. until you reach 2 to the n minus n and you get 0. Okay. Until when do you want to repeat the process? N times. But the problem is now I cannot repeat this process because uh, the q. Okay, actually you can repeat because there's only one symbol. Okay, you can simply repeat this process. Okay, that's not a problem. So now what do? You do the same thing now. You now that you have this 2 to the n minus 1 is, you take 2 is, pop them, bring 1 a here. You take the next 2 a's and pop and put a, and so on until stack is empty. Okay, and therefore by this procedure you will have uh, if only a single a remains in any process, then we obtain an odd number. If you obtain an odd number, it means it was not a power of 2. Okay. Okay, so now what we've observed is that a to the 2 to the n is, it is possible to use it here. C. Okay. Now the question is, which of the following statements are correct? Select all that apply. All CFLs are PTLs. All CFLs are PTLs. The answer is yes. Why? Let's look at CFLs. CFLs are those languages which can be accepted by PDAs. Okay. Now PDAs is nothing but you have stacks, and PTLs is almost the same, but now you have a queue, almost the same definition, but you have a queue now. Point is, a queue is a more powerful data structure than stack. The answer is that if uh, you can if you push the elements, okay, into the queue as if it were a stack. How do you do that? Well, um, let's say this is some A, B, C, D, okay, and in a queue, pushing would be uh, as follows: C, B, A, okay, and this is how. And in a stack, you want to simulate popping A here, but you cannot pop A directly. What you will need to do is first pop D, put it at the back, pop C, and put it at the back, then pop B, then put it at the back. B, C, D, and A remains. And finally, you get A, that is what you will be popping from the stack, essentially. Now we get this BCD, right? BCD, DCB. Observe that even after popping, okay, and pushing at the back, this is what we finally obtain. I mean, if you had popped A, this DCB is what we've obtained, and even after popping A, this is DCB is what we obtained. So this is still simulating stack. Stack can be simulated. Okay, stack can be simulated. because we need to pop A. Okay, so since stack can be simulated, entirety of PDA can be simulated by a push through Automata. So therefore, all CFLs are PDLs. PDA can be simulated by a PTA, which implies CFL, which PDA accepts, uh, is contained in PTLs, or CFLs are PTLs. Next, all PTLs are CFLs? Clearly not. Cannot happen. Why? Because we clearly know, we've seen all CFLs are not PTLs. Why is this the case? Because we've already known that WW is not a CFL. But we've seen that this is possible just recently. So clearly all PTLs are not CFLs. That means there are CFLs which are not PTLs. Same thing. Now the question is, there are PTLs which are not CFLs. There exist PTLs that are not CFLs, and that is the answer. I mean, that is the same thing here. This is a CFL, this is a PTL that is not CFL. Okay. Okay. So here's the question. So we've done with the Q automata, which is PTL, PTA. We'll now focus on the two-stack PDA. What can be done and what cannot be done. So here are some other interesting questions. Okay. Now we have two stacks. Remember. First question is A to the N, B to the N, C to the N two-stack PTL, PDL, two-stack CFL. I think that's what they call it. Okay, they don't have a language for this. So can this be accepted by can we design a push-down automata with two stacks that will accept this language? That is the question. And let's try for A to the N, B to the N, C to the N. So here is the idea. As we see A, I have two stacks. Stack A, stack B. I'll keep pushing A's. Now B's. I'll keep pushing B's as I see B's. Keep pushing A's. Keep pushing B's. In the after seeing the first portion on A to the N, on B to the N. When reading this portion, we do this, and when reading this portion, we do this. Okay. Now, what do you want to do? For C's, for encountering C's, for each C, delete or pop from A, from stack A, and pop at the same time pop from stack B. Okay, you may already notice that why this is correct. Say the input is A, B, 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 C, C, C. What do we do in the stack A? We push A, we push A, push A. In the second stack B, what do you do? We push B, and we push B. Now on seeing the first C, I will on seeing the first C, I will pop A. I'll pop a B also. I'll pop A. I'll pop a B also. I'll pop A. I'll also pop a B. And both the stacks are empty. Then accept. But even if one of them was different, even if there are more C's, then you can observe that at the end the stack would be non-empty. Oh, I mean, if there are more C's, then you cannot pop. You cannot pop further. More C's, then you cannot pop further. So that is the problem. At that case, you reject. Cannot pop further. Then reject. What does this mean? There are more C's. If there are more A's than B's, then what will happen? Then stack B will be empty before stack A. More A's than B's, then stack B gets empty before A. If this happens, then we'll define it to be reject. Then we'll design it so that we reject it. And similarly for if more B's compared to A's. That fine? Okay. So this is okay. So we know that we can construct a P to stack PDA for this. Now let me okay. So let's try this: A to the N, B to the M, C to the M, D N. A to the M, B to the M, C to the M, D to the N. Okay. How do you do this? Interestingly, you don't even require two stacks for this. Oh, okay, wait. Okay, these are symbols actually. They are not in simple stuff. N and M greater than or equal to 0. A, B, C, D are symbols. Yeah, interestingly, you don't even require two stacks. How do you do it? Well, push A's, push B's. A, and so on. Push B's, B, B, and so on. Okay, push A's and push B's. How many A's are there here? There will be n A's for a good string, for a string that is in the language. There will be n A's and there will be m B's. If top of stack has B and input okay, current symbol is a correct word. Current symbol is C, then pop. What does it mean? A, and so on. And B's were there, right? If I see a C, then I'll pop. If I see a C, then I'll pop, and so on. On seeing C's, pop. What happens if there are more C's? If there exists more C's than B, then what happens? Then I'll pop out, either I can define it in several ways. If I say, okay, then reject. I'll just directly say reject because I can just check whether B is if I encounter a symbol C, that is um, symbol on input equals C, whereas top of stack is B. Right. So I'll this is the logic here. So I'll keep doing this, and if it's a good instance, what will I get? A, and so on till A. Till how many A's are there? There are exactly n A's are there. When does this happen? When does this happen? This happens when number of C's equals number of B's. When number of C's equals number of B's. Then all the B's will get eliminated to give us exactly n A's. Now, once n A's are there in our hand, what we simply do is simply pop if we see whenever we see these. Pop, pop, and so on. Well, what happens if there are more D's than A's? So number of D's is greater than number of A's. What happens? Then stack is empty. Then we have more D's. No, stack empty before entire input is read. So in such a case, we can design the PDA, okay, to reject automatically. And similarly, you can ask what happens if number of D's is strictly less than number of A's. So that means the stack is not empty. The stack is not empty when the input ends. In that case, you trivially reject. So these are the kind of things you can say. But what is the essence of it all? What you're doing is you're simply putting a layer of A's of length n, then you're putting a layer of B's of length m, then you are seeing C's, MC's, then you just keep popping B's, because we know that a good B will always have length m. Only if B and C are equal will this top part get top part get destroyed, and only if D and A number of D's and number of A's are equal will the bottom block get destroyed to make the stack empty. And whenever the stack is empty, the input is getting accepted. Okay. Okay. Okay, so this part is also done. So let's look at the next one. A to the 3n, B to the 4n, C to the 5n. Okay. How do we deal with this? Let's try. Let's say we put all A's here. And we have two stacks, remember? And let's say we put all B's here. Three n, 4n. Next, what can you do? Well, C's, how will you deal with C? Now, if you say for each C you will pop A's, and then how many C's will you eliminate? You will eliminate 3 NC's. So how much remains? 2 NC's remain out of 5n. So with the 2n, how do you compare 4n? And such kind of questions will come up. So question is, can you come up with a clever method? Okay, it's more like a puzzle in this case. Can you come up with a clever method to um, achieve this. Okay. So here is one method. So I'll do it step by step. In the first step, what you do is push all A's onto the stack, on stack A. Step 1. Push all A's. What is the length, or what is the size of the stack now? 3n. Okay. Next, what do you do? Step 2. Pop all A's and push B's. Okay. Push B's here in B. Pop is for each B encounter. For each B, pop is when? Until when? Until A is empty. Until stack A is empty. Okay, if I see a B, then I'll push in the first stack, I'll just pop A's, and in the second stack, I'll push a B, and so on. Next, let's look at step 3. What will I do? Push. So what becomes the length of this? Since we've popped until all the A's are exhausted, so we have 3 and B's here. Okay. Next, what do you want to do? What we'll do is now we'll push B's onto, okay, when input sees B's. We'll push B's onto both A and B, stacks A and B. So what do you get? How many B's were remaining? There are a total of 4 n B's, out of which 3 n B's you've put. So there are exactly n B's remaining. So you'll put B here, you'll put B here, and so on. In stack A, since remember stack A is empty, so now it becomes n. And now stack B. For stack B, you already had some 3n B's. You're pushing n B's more, B's and B's. What is the total? 4n. Okay, and you have n there. Now what do you do? Final step C. Step 4. That is while seeing C's. What do you do? You pop from A until A is empty. How many do you pop? So this is A, right? A's size was n. So popped n many times. What does it mean? We've seen, this means we've seen n C's so far. How many C's do you mean? Step 4, 5. 4 n C's remaining. Right. 4 n C's are remaining. What do you do? Pop all B's from stack B until you see C. B, right? Pop. How many were there? 4n. Exactly 4 NCs were remaining, exactly 4 NPs were remaining in the stack, and 4 NCs were remaining in the input. So stack can only be empty. When can the stack be empty? At the end, when input is of the form a to the 3n, b to the 4n, c to the 5n. Okay. Is it done? Okay. Yeah. Now the final part is a to the n, b to the m, c to the n, d to the m. Now this language is pretty simple compared to the previous one. A to the n, b to the m, c to the n, d to the m. Okay. That is, number of A's is equal to the number of C's. What do you simply do? Procedure is simple now. For A's, push A's onto stack A. For B's, push B's onto stack B. Now what do you do? Simply when you see a C, you will pop from A and from stack A. And if you see a D, you will pop from stack B. So you have A and you have B, okay, and you have A's here and you have B's here, right? And how many A's do you have? You have N, you have M here. So when seeing C's pop from stack A, when seeing D's pop from stack B. Getting it? Now, if number of A's equals to number of C's and number of P's is equal to number of D's, yeah, then both stack become empty. Then accept. And the automaton accepts. Okay, good. Yeah, so this is done. Now we've completed all from the 4 languages, right? So yeah, so here's the final question from that section: is that which of the following automatons can be used to recognize a PTL? Recall what is PTL? PTL is PDA with a Q. Okay. Now select all the correct option. A 2-stack PDA, a 2Q PTA, okay, a standard PDA with 1 stack, and an NFA. Now clearly an NFA cannot do it. NFA cannot, because PTA is much more powerful. Example, WW is in PTL but not regular. If it is not regular, it means no NFA for the problem. What about a standard PDA with one stack? A standard PDA with one stack. Is it possible? No. We already showed this. This is not possible. Why? Because something like WW again is not CFL. Okay. Now, a two-stack PDA or two-queue PDA. These are the only options remain. A two-stack PDA. Let's look at it. Question says, which of the following can be used to recognize a PTL? Which of the following can be used to recognize a PTL? Again, the question is asking, okay, whether a push-through automaton or a two-stack PDA can be used to simulate a push-through language. So a two-stack. Okay, let me reiterate that. Okay, can be used to recognize a PTL. So PTL is supposed to be the weaker. Question says, can PTL be recognized by two-stack PDA? This is the question. Can push-through language be recognized by a two-stack PDA? So in other words, can PTA push-through, that is PDA with a queue, be simulated by a two-stack PDA? Remember that this is PDA with a queue. And the answer is yes. Why? Remember that this has two stacks and here is a queue. There's a fact, okay, there is a common data structure exercise that says that any queue can be implemented using two stacks. Any queue can be implemented using two stacks. How? Say, so this is the stack A. I have two stacks A and B. So I want to simulate A, B, then I want to simulate push C. This is a queue. How do I do that? Oh, I can just put A, B, and then push C. So push can easily be done using a stack. Okay, push can easily be done. Next, I want to pop. Okay, how about pop? Push is easy. Now, there is a non-triviality. What? Pop can only be done at the front. So, if I have A, B, C, that is my new. And what does the stack look like? A, B, C. This is the stack. I have two stacks, remember. Now, popping should remove A. Pop A. How to do this? We'll simply transfer to stack B First C will be transferred, then B will be transferred, then A will be transferred. Now, since it is a stack, I can pop it from the top, pop A. Now what do I get? Okay, then I just get BC. Now what I'll do? Transfer to stack A. When I transfer, I get B here, then I get C here. So if I think of it as a queue, on the front I have B, then I have C. This is exactly what I wanted. Okay, so any queue can be simulated by two stacks. Now there is a final question. Okay, so this is true. Now the question is, can a 2Q PTA be used to recognize a PTL? So what does it mean? What does PTL mean? So nothing but a PDA with queue. How many queues? One queue. Question is simply saying, can you do a task that requires one queue by a machine that uses two queues? But that is easily done because you are telling me to do a weaker task, right? So PDA with one queue, okay, can be simulated using a PDA with two queues. How can you do it? Well, the reason is that you can simply use one queue. If you have queues A and B, just use A and act as if you are doing a PDA with one queue. So obviously any PDA, obviously any PTA, this is nothing but PTA. Obviously any PTA can be simulated by a QPTA. So this is trivially possible. Okay. So that with that we've solved the questions. We've solved the tougher questions on the tougher side from week number 5. Well, I would have liked to do a few other questions also, but yeah, it's almost time. Although we have some 20 minutes, but anyway, this is a recorded session, so there is no live audience. So maybe I'll save the questions for later. So this will be recorded for later purposes. But an announcement would be that the remaining sessions will be back on the original timings, which is Tuesday 6 p.m. All right. So Tuesday 6 p.m. will be, so for example, for the coming week, that is the 5th of March, will be the next session, week 6 session. Okay. Yeah. So with that, I'll end this session. I'll end the recording. Okay. Thank you.